Hey students, welcome to lecture number 13 of Linear Algebra 1. So last time we introduced the notion of orthonormal basis for a subspace in Rn, and this was just a basis where these basis vectors are pairwise orthogonal and each of these vectors have length 1. And today we want to give some application for this concept. And so the topic we are going to talk about today is orthogonal projection and the so-called least square method. And before we do this, I want to give some motivation for this, because this has a lot of application. So, for example, assume you have some measurements. Let's say you measure something at some points. Let's say x1, x2, x3, x4, and let's say for each of these values. So assume we have some data points, x1 with y1, x2, y2, x3, y3, and x4, y4. So let's say here I have y1, let's say here's y1, maybe here's y2, maybe here's y3, and maybe here's y4. So here's y2, here's y3, and here's y4. And you maybe know that that these points should describe something which is usually given by some linear function, but your measurement is maybe not accurate. So what you want to find is somehow the best fitting line through these points, because at first notice that they are actually not on one line here. So for example, these 2 points, they are on one line, but these two are not on this. But you somehow see that the growth of this thing here, so the function which describes these data points, could be maybe this line here, or maybe this line here, and the difference here between the points and the actual line is maybe just some failure which comes from your inaccurate measurement. And and the question is, how do you find actually the best fitting line through these points? And the answer will be by using orthogonal projection and this least square method. But first we need to translate this problem here into a linear algebra problem. So let's assume that these points are actually on a line. So assume these are on a line. I mean, in the picture they are not, but if they are, so let's give the line name. Let's say we describe a line, maybe use some color here. Let's say we have a line L of x, which is given by some ax plus b. Yeah, so this would describe a line like this, and let's assume that all these 3 points lie on the graph of this function here. So this would mean that, for example, ax1 plus b is the same as y1, and ax2 plus b equals y2, and ax3 plus b equals y3, and ax4 plus b equals y4. Yeah, so if they are all on the graph of this function here, then if I plug in x1 in this function, then I should get the value y1, and so on. And this here we can write as a matrix, right? Because on the right hand side we just have the vector with these y values, and on the left we can think of this as multiplying a matrix with a vector AB, and here we have 2 columns which corresponds to this here, and here in the first column we just have these values x1, x2, x3 and 4, x2, x3, x4, and in the second what do we multiply b with? Well, here is just the number 1, so here you have 1, 1, 1, 1. So if these 4 points are on a line, which in this picture they are not, but if they are, then they satisfy this linear equation here. So in other words, we can solve this linear equation, so we can find A and B if they are on a line. So maybe let's first write this differently. Let's maybe call this vector here y, and this vector here we call maybe just AB. So they are on a line. The points on a line. Then what does this mean? Well, then this means we can solve this linear equation, and this means that this vector here is in the image of this matrix here, where by the image of a matrix we just mean the image of the corresponding linear map. So if I send a vector AB to this matrix times this vector, this is a linear map, and therefore we can define what we mean by the image of this. And if this vector here is in the image, then this by definition means there is a vector AB such that A times this vector AB equals this vector. So we can say that AB, this vector, this vector y, not AB, is in the image of A. But in this picture here, the corresponding vector y is actually not in the image of this matrix A, because these 4 points are not on a line. I mean, these 2 points are on a line, so if I would just forget these values here, then I could solve this linear equation. But if I add this point here, then this equation here has no solution. Otherwise, this equation here has no solutions. So this means they are not on a line. But we somehow want to find the best possible solution. So if this has no solution, we can see in the picture that there might be a best possible line. So what is the best possible values for A and B, which for example describes this line here. And this is what we want to find today. And the main idea is, so first of all, but we can ask for the best possible solution of this linear system here. And what will be the main idea? Well, the idea is if y is not in the image, so maybe let's draw a picture here. So let's say this is the image of A. Well, I just draw it now as a line, but usually, for example, here it will be something in 4 dimensions, which I cannot draw, but let's assume this is the image of A. And if y is not in the image, then y is maybe somewhere here. And this equation here has no solution if on the right hand side we have something which is not in the image. But we want to find the solution of this equation here. And what we do is we want to replace the right hand side here by something which is in the image of A. But we want to find somehow the best possible solution. So what we want to find here for the right hand side is the element in the image of A which is the closest to this y here. And if you look at this picture here, what is the closest point on the image of A to this y? Well, this is exactly what we considered last time. So last lecture, if the image of A, which is a subspace, we called U, and then we saw that for each element in Rn, so this y is an element in Rn, we can find here this point, which we denoted by y a parallel. And this will be the orthogonal projection of this point y on the subspace U, or in this case the image of A. And so the idea is project y onto the image of A, So this will give us a vector y parallel, which is now inside the image of U, the image of A, sorry. And this has the property that this is the closest point to the original y, which sits inside this image of A. And then what we want to do is solve for this equation here, A times this vector AB equals this orthogonal projection. And this we can solve because the right hand side here is in the image of A, and therefore this will give us a solution, so we will get some numbers A and B, and these A and B are somehow the best possible solution of this original linear system, which had no exact solution. But if we draw the corresponding line here with these A and B, the solution of this solvable equation, then we will see that we get exactly this here. And this will be called least squares, because this solution here, the property will be that if I consider the differences here between these points, then if we sum all these up, then this will be minimal. And so more precisely, we will see that if we take the this vector here and the distance here, which is given by the norm, and the norm is the square root of the sum of the squares of the entries, and if we take the difference of the squares, then we will just minimize exactly the difference between these points and the line. And because we sum up the squares, this is called the least square method. Okay, so this will be the plan today, but before we can do this, we will need to talk about this orthogonal projection. So last lecture we actually introduced already this y parallel, and for this, to calculate this, we said that if U has an orthonormal basis, and we learned that every subspace actually has an orthonormal basis, then there was an explicit way of writing down this y parallel. But we will see at the end of the lecture today that we actually do not need to calculate an orthonormal basis, and there will be a really nice and easy way of calculating the solution of this solvable thing here. Okay, so let's start. So first of all, recall what I just already mentioned, namely this corollary we did last time. So if U is a subspace, then for all vectors in Rn, they exist unique, this x parallel and this x orthogonal, where this x parallel is on the subspace, and this x orthogonal is in the orthogonal complement. So here the orthogonal complement of U is somehow this thing here, such that this x can be written as a sum of these two things. So in this case here, I can find a vector y parallel such that this vector here is this x as a y. So this here is y orthogonal and y parallel, and this y is a sum of these two. And the statement of this corollary is that they are unique. And the proof was that we first needed to show that U has an orthonormal basis, and then there was an explicit formula to write down this element here. And we learned that U has an orthonormal basis because there was this Gram-Schmidt algorithm which gave a method to explicitly construct an orthonormal basis. And what we want to define now is this orthogonal projection, and what this map will do is it will send, so given a subspace U, the orthogonal projection will send x to this x parallel. So it will exactly do here in the picture, will send this y onto the subspace U. And this is the first definition. So if U is a subspace, we define the map PU, which is a map from Rn to Rn, which sends this x to this x parallel, where this x parallel is the one given in the corollary. And this is called the orthogonal projection onto U. And notice that this we already did for a special case, namely if U is the span of some vector U, so u was a vector in Rn, which is not the zero vector, then this new orthogonal projection is exactly, so here this is a small u, what we denoted before, p small u. So we just defined this orthogonal projection for the case when u is a one-dimensional space spanned by some small vector here, some small u in Rn. So this is now the general version, because now we allow arbitrary subspaces. So for example, u could be a plane or some higher dimensional object and not just a line. So here, so this is as before. And here the difference is this is a capital U, the name of the subspace, and this is here the small u, the name of the vector. And this notation we used before. And for this orthogonal projection, for this special case here, we proved that this is a linear map, and that if you apply it twice, then it's the same as just applying it once. And similar statements also hold now for this general version. So for an arbitrary subspace U, this PU is a linear map. Then the second statement is if I apply PU twice, this is the same as just applying it once, which makes sense because if I project something on something and then try again to project it on the same space, then nothing changes. So applying it once is the same as applying it twice or 3 times, 4 times, and so on. And the third statement is that the image of this orthogonal projection is exactly U, which is clear because this x parallel is in U, and I can also find every element in U, because if I start with an element in U and I apply the orthogonal projection, then it just stays the same. And the kernel of the orthogonal projection, well, if this here is 0, then this means that the x, the original x, is given as an element in the orthogonal complement, and therefore the kernel of this orthogonal projection is exactly of the orthogonal complement of the subspace U. And then the last statement is that if we have an orthonormal basis of the subspace U, which we denote by f1 up to fm, then this orthonormal projection can be written down explicitly by this formula here. And this is what we did last time, because this was exactly the formula for this x parallel. And also compare this to the special case if U is a span of a small u, then this PU was given by the U, the dot product x, and then we divided by U times U and multiplied by U. And so you see this, so if we forget this part here, it's almost the same. But now here we have the condition that this FR is an orthonormal basis, meaning that the dot product of one basis element with itself is 1. So here in this case, this because the space U is spanned by this vector U, and therefore U is a basis of this space, but it's not an orthonormal basis. But if the norm of U is 1, then this is an orthonormal basis, but this just means that this vector here is 1, and then if you look at this, if you would call this U F1, then this is exactly the same formula here. But the general formula just says that you just need to add this term for each of these basis vectors. And this here we explained last time. And from this formula, you can also see that this is a linear map, similar to the way you proved that this here is a linear map. So you just need to check that these two conditions are satisfied. But this follows directly from the properties of the dot product. And also that if you apply twice, so this for this special version you did this as a homework, but this also works for this general version. So therefore I will not give the detailed proof of this proposition, because it's quite similar to the special case. And now the following thing, which also, if you draw pictures for this scenario, it's somehow clear, but maybe in formulas it looks more complicated than it actually is. So if I have a subspace U and I have some vector x, so maybe let's again draw this simple picture here. So U, this is a subspace, where in the picture it's a line, but in general it could be a plane and something else. And I start again with some x. Then the statement is for all U in U. So for example, if I here have some U in U, the statement is that the norm of x minus pu, so what is this vector here? So first of all, pu is, so here is pu, oops, p capital U of x, and x minus pu is exactly this vector here. And there we take the norm, so the statement is the norm, or the length of this here, is smaller equal to the norm of x minus u, so this thing here. So the statement is that the distance of x to points on u, so to any point on u, is always greater equal to the distance of x to this orthogonal projection, which is also in u. And the only case where we have equality here is when this u here, which can be element in u, any element in this capital U, is precisely this orthogonal projection here. And this I will not prove in general, but I hope that this picture makes clear that this statement here makes sense. So if I have an element x outside of some subspace, so if I have, let's say I have a plane here and I have a point, and I ask you which point on this blue plane is the closest to this point here, then the answer will be, well, we need to take the orthogonal projection, and then this point on the plane is the closest to this point here. Okay. So, and as I said in the motivation, this is what we want to calculate, because in our application this U will be given by the image of some linear map, or it will be the image of some matrix, and we want to solve the linear equation where this vector here is on the right hand side of our linear system. And but this will have no solution if this vector here is outside of U, but we want to find this point here, because if this here is on the right hand side of our linear system, then we will have a solution because it will be in the image of this linear map. And but if we are just interested in this the solution of our linear system and not actually in this point here, then we will see that that we will not need to calculate an orthonormal basis, and we will not need to calculate this point here actually. But to see this, we first need to understand. So recall, we will be interested in U being the image of some linear map, or being the image of some matrix A, where A is now the matrix of the linear map F. And therefore what we want to understand to get to this point here is the orthogonal complement. So this will lead to that we will be interested in the orthogonal complement of the image of a linear map. And there will be a nice description of this image, the orthogonal complement of the image of a linear map or a matrix. And for this we need to introduce the notion of the transpose of a matrix. So maybe some of you already know this. So if I have a matrix, M times N matrix, so a matrix with m rows and n columns with entries a, I, j, then the transpose of this matrix, which is now written as AT, is given by the n times n matrix, so here this is reversed, with the entries a, j, I. And what this just means is that I change rows and columns. So if I have a matrix A, 1, 0, minus 1, 2, 3, 4, for example, so this is a 3 by 2 matrix, then the transpose of A, the first row will be just the first column of A, so it's 1, minus 1, 3, and the second row will be just the second column of A, so 0, 2, 4. And this will be then a 2 by 3 matrix. Okay, and so this transpose satisfies a few easy to check properties. So first, if I have two matrices of the same size, then for example I can add them and take the transpose, and this is the same as first taking the transpose and then adding them, which is hopefully clear by definition. And because adding just means each entry I add, addition is defined component-wise, and if I have some number lambda and I multiply it with the matrix A, just meaning I multiply each entry and take the transpose. This is the same as taking the transpose and then multiplying with this lambda. And so I hope this property here is clear. And now if I take the product of two matrices, so if I have an m by n matrix, then this matrix I can multiply with an n by l matrix. So recall that this number here, so the number of columns of a matrix A, needs to be the same as the number of rows of a matrix B in order to multiply A with B. So in the end, this will be an m times l matrix. So if I take the transpose of this product here, then this will be an L times M matrix. And the statement is that this is the same as taking the transpose of B first and then multiplied with the transpose of A. So the transpose of B is a L times N matrix, and the transpose of A is an N by M matrix. So these I can multiply, and the result will be an L times M matrix. But the important point here is that you need to change the order. And this, maybe it's not as obvious at this property here, but if you maybe do an example for yourself, you see that you need to change this order here. In particular, if m and n and n and l are not the same, then if you wouldn't change the order, this wouldn't be defined. But you also see, if you write down the product of a matrix, of these two matrices here, that this is indeed correct. So similar to the inverse, recall if A and B are square matrices which are invertible, then and in order to take the inverse, we also needed to change the order of these matrices. And then the last point, which will be important for today, is that the dot product of two vectors, which appeared several times now, is just given by the transpose of x with a vector y. And because this is also clear, if I have a vector x1 up to xn and a vector y1 up to yn, I mean, what is x transpose? Well, this is just the 1 by n matrix, x1 up to xn, and therefore if I multiply this with a vector y, then I get this here. And how do I multiply this vector with this matrix? Well, I just need to multiply y1 with x1, y2 with x2, and so on. So this here is exactly this. And this was exactly the definition of the dot product of these two vectors. Okay, and why do we introduce this notion here? Well, the reason is because of the following proposition, where the statement is that if I have a matrix A, an m by n matrix, then the image of A, meaning the image of the corresponding linear map given by multiplication with A, the orthogonal complement is the same as the kernel of the transpose of the matrix A. Okay, so first of all, if A is an m by n matrix, so this means the corresponding linear map is a map from Rn to Rm. So therefore this here is a subspace in Rm. And the A transpose is an n by m matrix. So this gives the linear map from Rm to Rn. And therefore the kernel is also in Rm. I mean, otherwise this statement wouldn't make sense. Okay, but now let's see why this is true. So if we want to calculate the image, the orthogonal complement of the image of a linear map, this is the same as calculating the kernel of another linear map, and this other linear map, the matrix of this other linear map, is just a transpose of the original matrix. Okay, so let proof. So this will now be several steps. So we want to say that we want to see that any element here is also an element here, and vice versa. So we will start with an element in the image of A in the orthogonal complement. So this means that this x is orthogonal to any element in the image of A. So meaning the dot product of x with y is 0 for all y in the image of A. So this is a definition of being in the orthogonal complement of something, that this element x is orthogonal to all elements in this something, and in this case the something is the image. And if y is in the image of A, what does this mean? Well, this means that y is given as A times some vector v, where v is some vector in Rn. Yeah? Because being in the image means there is some vector v which gets mapped to this element y. So this means that x is orthogonal to all these vectors here. So x dot product A v, or we can also write it the other way around. It doesn't make, because the dot product is commutative. So this is true for all vectors v in Rn. Yeah, because x is orthogonal to all elements in the image, and every element in the image can be written as A times some vector v. And now we can use what we saw before, namely that the dot product can be written as transpose times something. So instead of writing the dot product here, we can now say this is the product of the transpose of this vector AV with x, that this equals 0 for all v in Rn. And now we can use the second statement here, that taking the transpose of a product, I mean here I write it with matrices, but a vector is also a matrix, so here I can also use this rule that the transpose of this product is the same as taking this here. So Rn. But now we have V transpose times something, and we can use again that this we can write as a dot product of these two guys for all V in Rn. So now the statement is that this vector here, A transpose times X, is orthogonal to all vectors in Rn. So this means that this A transpose X is in the orthogonal complement of Rn. But what is this? So which vectors are orthogonal to everything? Well, there's just one vector, namely the zero vector. So this here is just the space containing the zero vector, and therefore, if this is inside the space, the only possible way is when this is 0. So therefore, A transpose X equals 0, and this is the definition of X being in the kernel of A transpose. And this is what we wanted to show, because now we see that if X is in the orthogonal complement of the image of A, this is equivalent of X being in the kernel of the transpose of A, because all ways here are equivalent. Okay, so this is this, and from this proposition we now get a corollary, namely the following, that if I have some matrix A, then the kernel of A is the same as the kernel of A transpose times A. And we will see later why this is interesting. And here the second statement is that the kernel of A is 0 if and only if this matrix here, A transpose times A, is invertible. And here noticed that if A is an n by n matrix, then A transpose times A is an n by n matrix. This is actually an n by n matrix, sorry. Because A transpose is an n by m matrix, and therefore if I multiply this matrix here with an m by n matrix, then the result will be an n by n matrix. But anyway, the important point here is that this is a square matrix, so for any matrix A, no matter what size this is, if you take the transpose of this matrix and multiply it with the matrix, then this matrix will be a square matrix. So, and for square matrices, we learned that this notion of invertible makes sense. And in this case here, this matrix is invertible if and only if the kernel of A is 0. And also notice that this basically means here that this corresponding map of A is injective. But A here in this corollary is not necessarily a square matrix, so it wouldn't make sense to say that A is invertible. But this here is always a square matrix, and therefore we can say it's invertible. Okay, so let's prove the first statement, that the kernel of A transpose times A is the same as the kernel of A. So again, we do a similar calculation. So we start with X being in the kernel of A transpose A, and this by definition means that A transpose A times X equals 0. And this means that if I multiply this stuff here with A transpose, it's 0, and therefore this means that AX is in the kernel of A transpose. And in the proposition before, we saw that the kernel of A transpose is exactly the image of it's the orthogonal complement of the image of A. And therefore, AX is in the orthogonal complement of the image of A, but AX is also in the image of A, because that's the definition of the image of A. It's all the possible outcome I can get by multiplying with the matrix A. So therefore AX is in the image of A, but it's also in the orthogonal complement. So this means that this AX is in the image of A, and so this is the intersection of the orthogonal complement. But we learned last time in lemma 12.5, I think, that the intersection of a subspace with its orthogonal complement is just the zero vector, and therefore in this case this here needs to be 0. AX equals 0, and this means X is in the kernel of A. And this proves the first statement, where we wanted to show that this kernel here is the same as this kernel here, and we saw that if this is in the kernel of A, then it's also in the kernel of A transpose A. Well, this is clear because if I multiply this here with the vector x and AX is already 0, then everything is 0. But this direction here is not clear. But we showed that if this is in the kernel of A transpose A, then it's also in the kernel of A. And the second statement, so we want to show that this here is equivalent. So if the kernel of A is just the zero vector, then by the first part, because the kernel of A is the same as the kernel here, then the kernel of A transpose A is 0. And now we need to remember a theorem from lecture 8. So this here is a square matrix, so therefore this gives a linear map from Rn to Rn. And then we learned in theorem, so this is theorem 8.7, that if a linear map from Rn to Rn is injective, then it's automatically bijective. So this was a special case. In general, this is not true if I have a linear map from Rn to Rm, so two different numbers, and this is injective, then I cannot say anything about being bijective, surjective or bijective. But if it's a map from Rn to Rn, so in the same space, and I know it's already injective, then we learned it's automatically surjective and therefore bijective. And also if you know it's just surjective, then it's automatically injective. So this here is a square matrix, and therefore if the kernel of this is 0, this exactly means that the corresponding linear map is bijective. And this being bijective for a linear map means that the corresponding matrix is invertible. And therefore this thing here is invertible. And this also goes in both directions, because we learned that, well, this direction is easy. If this is invertible, then of course also the kernel of this is 0, and then also this kernel here is 0, because by the first part. Okay, so this is this. And this now we want to use to solve the original problem in the motivation part. So what we know now is this important property here, that the orthogonal complement of the image of a matrix or a linear map is given by the kernel of the transposed matrix. And also that the kernel of this matrix here is the kernel of this matrix here. And this matrix here is invertible exactly when the kernel of this matrix here is 0. Okay, but now let's reformulate the problem we want to solve. So the method we will then do is this least square method. So the problem is, given a linear map f from Rn to Rm and some vector b in Rm, so some vector here on the right hand side, what we want to find is a vector here on the left hand side, x, in Rn, such that this expression here, so f of x minus b, the norm of this, is small. And here we will call this delta. And this is the image I already drew 2 times. So if this is the image of f, or the image of the corresponding matrix A, and we start with some vector b, then we want to find an x such that b to f of x difference is minimal. So here this means we want to find, for any x we get a point here on the image of f, but we want to find in this case this here with a minimal distance here. So this distance here will be our minimal delta. And as we discussed before, so we had this one proposition which told us that all these points, the difference to this vector here, is bigger than this difference if this point here is an orthogonal projection. So what we want is that this f of x will be given by the orthogonal projection onto the image of f of this vector b. And so first notice, so I mean we want to find the minimal distance, but what could happen is that this b is already on the image of f, and this would mean that so we can say that the minimal delta is 0 exactly then when b is in the image of f. But this is hopefully clear. So if b is on the image of f, then it's somewhere here on the line, and then of course the delta here is 0. But in the other cases this here will be a non-zero. But we want to find an x which minimizes this. And the important point here is we want to find the x and not the f of x. I mean, to find the f of x, we could, for example, calculate an orthonormal basis of the image of f, and then we can use this formula, which we saw in one of this proposition, which is given by the sum over all basis elements in the orthonormal basis, and where the coefficients are given by the dot product. But this is not necessary. So first of all, so solution to this problem. So first of all, let's talk about matrices again. So let's just call the matrix of FA, and so we want that AX equals this here. So want to find x in Rn with AX equals the orthogonal projection of B onto the image of, okay, here we can also write on the image of A. So what does this mean? So what about the, so here this will be, I mean this is now AX, and we want to find an x such that this here holds. So in particular, if we have such an x and we get this point here, the difference of this point to this point here, so meaning this part here, this will be in the orthogonal complement of the image. So in other words, this is equivalent of that the difference of AX B is in the orthogonal complement of the image of A. Well, these brackets here we don't need. Yeah, so because this is vector here, if this AX is the orthogonal projection, then the difference of this point AX to the point P is orthogonal to the image of F, and therefore we have exactly this here. And now we learned, now this is why this proposition is so important, that the image of the orthogonal complement of the image of A is the kernel of the transpose of A. So therefore this thing here should be in the kernel of this matrix here, meaning that if I multiply this matrix with this, then we should get 0. So if I multiply this equation here with A transpose, then this should be 0. And in other words, we could write this out, so A transpose times A times X minus A transpose B equals 0, but this here I can put on the other side, so here I can just write A transpose B. So therefore, the vector X we want to find satisfies this equation here. So here we see we have a matrix times X equals a vector. And also notice that here we now have this A transpose A, and we had this corollary before, that this here is invertible if and only if the kernel of the original matrix A is not 0. Is just 0, sorry. So in general, so first of all, this here has a name because it's an important equation. So this is called the normal equation. And notice, so this is now, so this here is a square matrix, and a square matrix times vector X equals this. And A and B are the input of our original problem, because A is a matrix of F and B is just a vector which we are given. And therefore to find this best possible X, I mean usually this equation here will not have a solution. So we will not find the solution because B is maybe not in the image. But this here, this will have a solution in the most cases, namely in those cases where this matrix here is invertible, and we saw that this is the case when the kernel of A is just 0. So therefore we can say if the kernel of A is just a 0 vector, which in most cases will be the case, because for example, recall that at the beginning, here we had this matrix. In the most application cases, we will have more rows than columns, and the kernel of this matrix here being 0 just means that the columns are linearly independent. But if you think about this, if I usually have more rows than columns, then in most cases these vectors will be linearly independent. Especially here you see that already if x1 and x2 are not the same, then these two columns are linearly independent. And therefore the corresponding matrix A transpose A in this example here will be invertible, and then we can solve this equation we just described, this normal equation, and this would give then values for A and B. So then get the unique solution. The best possible X is given by A transpose A inverse times A transpose B. Yeah, because if this here is invertible, I can take the inverse and multiply it on both sides, and then on the left I just have X. So therefore, given a matrix A and a vector B, I can calculate this expression here, and I will get the best possible solution for my linear system. Okay, so let's do an example for this. And so I will not do the line example from the motivation, but I will do something more general, or well, a special case. So I want to talk about polynomial or polynomial interpolation. So what this means is a similar example as in the motivation, but just instead of just considering lines, we can ask in general for a polynomial which maybe is the best fit for our data points. So in this case here, I want to find a quadratic polynomial, so a polynomial of degree 2, and the polynomial of degree 2 is described by 3 values, a0, a1, and a2. And let's say we have 4 points, like in this picture here, so 0, 2, 1, 1, 2, 2, and 3, 3. And what we want to find is now the best possible quadratic polynomial which goes through these points. But first notice there's actually no perfect quadratic polynomial going through these points, because these points here are already on a line, and you will see that there's actually no polynomial going through these points. And maybe in calculus you learned that if I would just give you 3 lines, 3 points, then there's actually one unique quadratic polynomial going through these points. But if I give you 4, then it could happen that there's no exact solution. So we want to minimize. Well, we want to find the best fit. So we want to find some f of t, which is maybe this here, which somehow minimizes these differences here. So to find which minimize this expression here. So f of 0, if I compare this to 2, which is exactly this here. So if I take the square and here, oops, this I can compare f1 with 1, take the square, and f2 with 2. So we want to minimize this expression here, and this is why this is called the least square, because we want to minimize these squares, or the sum of these squares. And this basically just means that if you interpret this as a vector in R4, then this here is basically the norm of the difference of these two vectors, except that we don't have a square root. But if you want to minimize something, then we actually can ignore the square root. So in this case here, so we want to find oh no. So what we do is, we define the following linear map. I mean, we now want to translate it to our problem here we described before. So this least square method. So we want to find a linear map where we want to minimize this expression here, and then we want to use this idea that we need to just solve this normal equation, and then this here will give us our best possible solution. So what we in this case here, what is the corresponding linear map f? Well, we want to find, so we have 3 parameters, this a0, a1, a2, and we send it to something in R4 because we have these 4 points. So we want to send it to R4, where we send this a0, a1, a2 to these values f0, f1, f2, F3. And so in this example here, well, F0 is just, we plug 0 into this thing here. So this is A0 plus 0 times A1, A1 times 0, plus A2 times 0, and F1 is A0 plus A1 times 1, plus A2 times 1, or more precisely it would be 0 squared and 1 squared, so A0, A1 times 2, plus A2 times 2 squared, so here it's 4, maybe let's write 2 squared, A0, A1 times 3, plus A2 times 3 squared. So in other words, this here is the matrix, so we want to send the vector A0, A1, A2 to the vector in R4, which is given by multiplying with 1, 0, 0. So here I just take now the coefficients of these A's, 1, 1, 1, 1, 2, 4, and 1, 3, 9. And this here we can call A, and this here we can call X. And what do we want to solve now? What is the vector y in our case here? Well, y are the values here. So what? So want to find x, which is this A0, A1, A2, such that this here ax minus b, with b being the values of our data points, so it's 2, 1, 2, 3. So here the 2, 1, 2, 3. I mean, we would like to have that f0 is 2, f1 is 1, f2 is 2, and f3 is 3. But this will not be possible because we cannot find the perfect polynomial. But we want to make this as small as possible. So we want to find an x such the possible outcome of the functions at these points 0, 1, and 2, and 3 are close to this 2, 1, 2, and 3. And this is exactly here the sum of these differences, because here are the values of our f, and these are these points we want to hit, but we will not be able to hit all of them, but we want to minimize at least these differences here, and this is exactly this expression here, except that this also is a square root of this expression here. But if you want to minimize the square root, then this just means you want to minimize the stuff which is inside the square root. So we want to find an x such that this expression here, where b is given by this and ax is this, is minimal. And therefore we need to solve the normal equation which I wrote down is A transpose A times x equals A transpose B. So we now just need to calculate all these expressions here by using all these inputs. So A, well, here I will steal A. Well, if this is A, what is A transpose? Well, A transpose means we change rows and columns. So this is 1, 1, 1, 0, 1, 2, 3, 0, 1, 4, 9. And what is B? B is this vector here. There's this vector. and therefore we can also calculate what is A transpose B, and we also can calculate A transpose A. Well, if you multiply this matrix with this vector, you get 8, 14, 36. So check that if you multiply this with this, you get this vector here. And if you multiply this matrix with this matrix, what you get in this case is a 3 by 3 matrix, a 3 by 3 matrix. So as we said, the square matrix 4, 6, 14, 6, 14, 36, 14, 36, I think 48. And now we can try to solve this equation here. A0, A1, A2 equals this vector. So this here is now A transpose A, this is X, and this is A transpose B. And this is now just a linear system, which we solved 1 million times during this lecture. Well, not this lecture, but during this course. And actually, in this case, we also know that this matrix here is invertible, because this matrix here, we need to check that these 3 vectors are linearly independent, which you maybe can see easily here. I mean, usually if I take 3 vectors in R4, the chances are quite high that they are linearly independent. But in general, these type of matrices where you write down these squares or these different monomials, then they are always invertible. But in any case, you can solve this equation here, and the solution, there's a unique solution given by 19 over 10 minus 11 over 10 and 1/2. So therefore, this tells us, here's again the 3 points, 0, 2, 1, 1, 2, 2, 3, 3, and here this orange line, so this is a best fit polynomial. The f of t we can read off now is the constant term is 19 over 10, which you can roughly see here. At 0 you are close to 2, so we are not at 2 here, but I mean this is almost 2, it's a little bit smaller, minus 11 over 10 times t plus 1/2 times t squared. And this graph here is exactly the graph of this polynomial here. And this is the best approximation of these 4 data points as a polynomial of degree 2. And yeah, so that's all. And in general, if you have some data points, you could try, I mean in general, polynomial interpolation works for any degree like this. So if you have your points, let's say you have 100 points and you want to find the polynomial of degree 5, for example, which interpolates them, what you can do here, you start with a polynomial of degree 5, which has 6 numbers. And if you have 100 points, you will have here then a map from R6 to R100. So this will give you a 100 times 6 matrix, and these 6 rows, they will be linearly independent. And then you can do these calculations and calculate here the normal equation, and you will see that this matrix here will be just a 6 times 6 matrix, and you can solve this and you will get a unique solution for the coefficients of your polynomial. And yeah, so this is all for this lecture, and I hope to see most of you again in Linear Algebra 2. So in Linear Algebra 2, we will generalize a lot of things we did in Linear Algebra 1. So instead of just talking about the Rn, we will talk about so-called vector spaces in general, and then a lot of things like the notion of a linear map will be generalized. So for example, one example for a vector space is a space of all functions, because you can also add functions and you can multiply function with a scalar, and then you can also define the notion of a linear map satisfying these two conditions. And for example, one example of a linear map on the space of all functions is given by the derivative. And then we can also talk about the kernel and the image of the derivative and so on. And you can generalize a lot of these things to functions, which then have a lot of applications. But yeah, first you need to survive the final exam, and then we will see more. See you then.